Higher Physics Notes, Unit 2, Section 2, Forces and Charged Particles. In this final part, Part 3, we're going to look at particle accelerators. Well, firstly, the purpose of a particle accelerator is mainly research, in which a charged particle is accelerated to a very high speed and then made to collide with other particles in high energy collisions in order to produce yet more particles, which can then be studied. The diagram for particle accelerators is slightly involved, so I suggest that you pause the video while you copy down the diagrams. So here is the first diagram. This is a linear accelerator, or LINAC, and linear, of course, just means a straight line. So the particle here is being accelerated in a straight line, no curving, no circles or anything like that. So I suggest, if you haven't done so, you pause the video now while you take down this diagram. So let's look at what we have here in this linear accelerator. We'll begin at the far left, and you can see there's an S there, which is the source. And in this particular case, it's a source of protons. So the particle being accelerated here is a proton. That's that little red sphere that you see. Now, in order to accelerate the proton, we need to attract it to a negative electrode. And you can see there are 4 cylindrical electrodes, C1, cylinder 1, C2, C3, C4. And in order to attract the proton to electrode number 1, we obviously need to make that electrode negative. So you can see the blue negative sign there, and that's going to attract the positive proton. So that proton will be accelerated across, given kinetic energy by the electric field, because the proton source itself is made to be a positive electrode, an anode, and cylinder 1 is made to be a cathode at this stage, which is negative. Now, as you can see in the text immediately below the diagram, as the proton reaches the middle of each cylindrical electrode, the polarity of the electrode alternates so that it is always attracted as it arrives and repelled as it leaves. Now, that's important because if you go back to the diagram now, when that proton is attracted across to the negative cylinder 1, that's fine, it's going to be speeding up. But as it gets halfway and it's now beginning to leave cylinder 1, because cylinder 1 is negative, that's actually going to attract the proton back again from whence it came. So when it reaches the middle, what we need to do is we need to change the polarity of cylinder 1 to become positive so that we repel or push the proton out to keep up the acceleration that it's achieving. So when it leaves cylinder 1 by this point has become a positive electrode. We then need, there's a little gap, as you can see, and this is all done in a vacuum. And as it travels across that gap, it needs to be attracted to the next electrode. So at the point of entering cylinder number 2, electrode 2, cylinder number 2 has to be negative. But then when the proton reaches halfway through that one, it then has to become positive as well to repel the proton out. And this happens at each of the electrodes. Now, it's all timed very, very carefully so that as a proton is arriving at electrode 1, a proton is leaving electrode 2. Now, the timing and the speed have to be very, very carefully synchronized to make that happen. But what it does mean is that whenever electrode 1 is negative, electrode 2 is then positive, electrode 3 then is negative at that point, and electrode 4 is positive. So the diagram shows you a snapshot in time at an instant. Now, as the proton moves through each electrode, it is, of course, gaining speed, gaining kinetic energy. It's getting faster. It's accelerating. It is, after all, an accelerator. So as it leaves cylinder 1, electrode 1, it's got a certain speed. When it leaves cylinder 2, electrode 2, it's going to have a greater speed. So as it reaches each subsequent electrode, it's entering that electrode faster. And that's why in the second bit of text here we say that each subsequent electrode is longer than the previous one. And the reason for that is if you look at the wiring now, you can see that we've got an alternating supply, and the alternating supply makes each odd numbered electrode the same polarity, so number 1 and 3 are negative, and each even one is positive, and then that alternates. So they all alternate at the same time, but because each subsequent stage has a faster proton arriving, because it's getting faster and faster with each electrode, it's going to cover a bigger distance in that same time. So if you imagine the period of that alternating supply to be t, the proton's going to travel much further during t at cylinder 4 than it is at cylinder 1. So the cylinders have to get longer as you go along. And the text at the bottom explains that for you. So that's the basic principle of the linear accelerator. And just before we leave it, if you look at the very top of the diagram, there's a voltage time graph there, and you can see that when electrode 1 is negative, the voltage goes below the x-axis to show you a negative voltage, and simultaneously the voltage at electrode number 2 is positive at that point. Notice that on the x-axis of that voltage graph is not time, but distance. So we're recording the voltage at that place in the accelerator as we go along. Okay, so at the end of it all, on the very far right-hand side of the diagram, you can see the proton emerging, and it's achieved probably relativistic speeds at that point. It can be smashed into other atoms to see what happens. So that's the linear accelerator, and that tends to be the one that features in past papers. There is also a non-linear accelerator called a cyclotron, and the cyclotron takes a beam of charged particles, typically protons again, and it makes them go in a circle. Now, if you look carefully, you'll see there's a magnetic field. B is the symbol for magnetic field strength. So those black arrows show a magnetic field coming up out of the page there. And the protons emerge into that field at the center of the kind of white circle. And if you get the speed and the strength of the field right, the curvature that we have previously discussed of the charged particle in the magnetic field can be made to be a circle. So it comes out, and if we look at the left-hand side of the circle, it's called a D, because it is a D shape. So that left-hand D, when the proton is in there, it's kind of curving round to the right, as you can see, and it goes round in a clockwise direction in a circle of a particular radius. But then when it gets to the gap between the two Ds, there is an electric field in there. So it's curving in its circular path because of the magnetic field. Right-hand motor rule would give you the situation. But when it gets to the gap between the Ds, and that's a very deliberate gap, this is all done in a vacuum, of course, there'll be a few centimetres gap there, there is an electric field placed across that gap in such a way that the proton is always attracted across the gap. So as it's leaving the left-hand D, the left-hand side of the D would be made to be positive to repel it away, and the right-hand side of the D at that point would be negative to attract it across. So there's an electric field in between the two Ds. Now, like any charged particle moving between positive, negative plates, it's going to speed up and gain kinetic energy. So it arrives at the right-hand D going a bit faster than it did when it left the left-hand D. Now, if you can imagine you're going round a corner in a car If you've got a very tight bend, that's a small radius, you need to go quite slowly, otherwise you'll skid off the road. Motorways, where the cars are moving really fast, always have very gradual bends with what you would call a big radius, because when you're going really fast, your radius of curvature has to be quite big. So when that proton comes from the left-hand D across to the right-hand D, it's accelerated through the electric field, that's between the Ds, the gap. It's faster in the right-hand D, therefore it has a bigger radius of curvature. So it comes round in the right-hand D at a bigger radius of curvature than it did when it was in the left-hand D. And then when it gets round to the gap again in the right-hand D, it's made to be attracted across the gap by the alternating current, which again is timed and synchronized to make sure we're always attracting it across the gap. And that makes it go even faster. So every time it goes round a half circle and goes across the gap, its radius increases. So its radius gradually increases with every half circle, and that's why the dotted line's kind of spiraling outwards. And then eventually, when it reaches the maximum radius of curvature, it's allowed to exit the cyclotron, and there you can see the proton being fired out, and there'd be a beam of these things, of course, and that can then be sent off to collide with other particles, and so on and so forth. So these cyclotrons are much more compact than the linear accelerators. They need to be very long and straight. These are packing everything into a much smaller space. And so there we have the two types of particle accelerator. It would be worth, because there's so much technical detail here, worth you going back to look at your course booklet on this material. It would be far too much to write down. So read your course book material in conjunction with these notes.